Okay, hello and welcome back. We are going to discuss local surface geometry. This will continue on from the last time, so let's remember that we have a an n-dimensional manifold, sigma, and it is immersed in an n plus k dimensional Euclidean space. And actually, for this purposes, we take n equals 2, k equals 1. So that we have a two-dimensional surface immersed by some function psi into R3. And we defined before a Riemannian metric, an induced Riemannian metric on this surface sigma by pulling back the Euclidean metric we'll call this delta. If I choose local coordinates, let's say U1, U2 are local coordinates on sigma, then I can write this metric as having components G11, G12, G21, G22. And of course, these two anti-diagonal terms are going to be the same because I have a symmetric matrix. And these coefficients are the Euclidean inner product of these partial derivatives. Right. Okay. So here we can abbreviate. Can abbreviate the partial derivatives this way. We discussed last time the connection Levy should be the connection. By writing the derivative. So this is, you should think of this as the derivative, directional derivative of y in the direction of x. So what do I do? Well, I take the ambient directional derivative, which makes sense in Euclidean space, and then I project onto the tangent space. So let's actually write out what this is. Now, what do we know? So I know that what is Gij? Well, this is the Riemannian metric applied to my tangent vectors d by dui and d by duj. So if I write my connection in local coordinates using these symbols, these things are usually called the Christoffel symbols. So you can think of this as just a representation of the, you can think of these symbols, these coefficients is giving you the local representation of the covariant derivative with respect to these coordinates. So what do I see? I see that, so the first thing I see is that that the Christoffel symbol is symmetric in the first two indices. But I also see that, well, what is, let's write it this way. So this relationship just comes from differentiating the definition of the metric coefficients here. When I do that, I find that this is going to be gamma gamma k I j plus gamma k j I. I can repeat this 2 more times. D I G J K is then going to be gamma I J K plus gamma I K J, and D J G I K is going to be gamma J I K plus gamma J K I. If I sum these 3 equations up, I will see that summing these 3 equations, we see that gamma I j k is 1/2 d k g I j. Gamma I j k is 1/2 dij jk plus dj gik minus dk gij. And then if I raise one index, I get this formula. So here are the entries, coefficients, inverse matrix of the metric. I use this to raise and lower indices. Okay. So what do we see from this? We see that even though we defined the covariant derivative in terms of or using the immersion, it only depends on the induced metric G. And in fact, this is what we use this formula to define the covariant derivative or the Levi-Civita connection on any Riemannian manifold. And we can do this without any reference to an immersion in a Euclidean space. Okay, so back to our picture. We have a surface immersed by some function psi in R3. We have our covariant derivative defined by taking the ambient flat covariant derivative and projecting onto the tangent space. The leftover bit this is the normal, the leftover bit will be the normal component. And this part we defined last time to be the second fundamental form. And we've shown this is symmetric. All right, so in the case of a surface, we can use the cross product to find and how do we write down this normal? We write this down as we take the cross product of our two tangent vectors. And then we actually want to normalize this to have unit length. This normalization is really kind of a convenience. Okay, so there are two important things we know. So first of all, we know that any tangent vector must have an inner product of 0. This is an ambient inner product, remember. With my normal vector. And as a consequence of this, what do we see? We see that if we differentiate this, we see this. This first term, remember, was our second fundamental form, and this whole thing had to sum to 0. So another way to write my second fundamental form is that it's minus the inner product of x with the derivative of the normal map in the y direction. We also know that my normal is unit length. So if I differentiate that, I see that if I differentiate that with respect to any tangent vector, I see that this inner product is going to be 0. And so in particular, I see that the derivative of the of the normal map must actually be tangent. And so in a way, you should think of, so in a way, what does this tell you? This tells you, first of all, the second fundamental form is, up to a sign, the tangent component of the gradient of the normal map. But we also conclude that the gradient of the normal map is entirely tangent to the surface. So actually, the second fundamental form gives you all the information of the derivative of the normal map. And this really gives us our notion that that the derivative of the normal map, the gradient of the normal map, captures everything about how the surface bends. So the second fundamental form captures all the information about how the image of this immersed surface bends in R3. And actually, this part generalizes to this generalizes to immersed submanifolds in Euclidean space. It tells you the exact same thing. The only thing that's a little bit more, you have to keep track of some more tangent directions and possibly some more normal directions as well. But otherwise, the idea is very much the same. So the way you can think about this is I have perhaps a piece of a surface sitting here. The normal vector is doing something like this. And what do I see? I see that if I move in this direction, the normal vector is going to be bending bending down and to the left. But if I move in this direction, I see that the normal vector is going to be bending this time. Oh, sorry. And if I move in this direction, the normal vector is going to be bending up and to the left. As I move in the other direction, it's bending down and to the right. So let's write some of this information. So we can write in components, local coordinates. I can write Hij is the inner product of di, dj, psi with n. And this gives us, this is a symmetric 2x2 matrix of functions on my surface. Okay, I can simultaneously diagonalize this with respect to the first fundamental form G. And then I get Hij is G JK HIK. And then I can take the determinant and trace. And even the eigenvalues. So these eigenvalues will be the principal curvatures. Okay, so what do these tell you? So let's remember what the eigenvalues are. The eigenvalues are given by a minimax characterization, namely that kappa 1 is going to be the smallest of, let's write it this way. So I can write the smaller of my two principal curvatures as this infimum of the ratio of these two symmetric bilinear forms, and then the larger I write as the supremum. And I do this essentially because I have really two directions. If I had a higher dimensional submanifold, then I would have a kappa 1 and a kappa 2 and a kappa 3, etc. And they would be given by, so the kappa 1 would be given by this infimum, and then the kappa 2 would be given by taking an infimum over two-dimensional planes within the tangent space, and then you take a supremum over that plane. So in this way, we see that these principal curvatures, kappa 1, gives the least direction of least bending, and kappa 2 gives the most bending. You have to take signs into account here. So again, let's draw a picture. So I see that in this direction, my curvature in this direction, so if I slice by a plane going through here like that, I have a picture where my kappa is negative. The curve is moving away from the normal. If I slice in the orthogonal plane with this red plane here, I see that the curve bends toward the normal. The curve bends toward the normal. So the curvature in that direction is positive. And so here we see we have the greatest possible curvature. This gives us the kappa 2, and the least possible curvature, this gives us the kappa 1. Okay. Then from basic linear algebra, we see that the Gauss curvature, the determinant, the determinant is right. So we see that the determinant is the product of the eigenvalues, and the trace, well, let's say the half the trace this is the mean curvature. Okay, we'll pause here for now, and we will continue next time with some examples where we work out what all these objects are for rotationally invariant surfaces.